Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The intellectual history of solid-state physics is punctuated by moments of profound neurochemical transformation, where a material once deemed intractable and obscure is suddenly rendered essential to the fabric of modern life. Few events exemplify this paradigm more potently than the work culminating in 1995 with Shuji Nakamura's announcement of high-brightness indium gallium nitride blue light-emitting diodes. This achievement was far more than an incremental improvement in optoelectronic engineering. It represented the solution to a decades-long quest, a challenge that had stymied the world's most formidable corporate and academic research laboratories. Nakamura's breakthrough, detailed in a series of publications around this period, effectively provided the missing cornerstone for solid-state lighting, completing the primary color triad and setting in motion a revolution in energy efficiency and digital display technology that continues to reshape our world. To fully appreciate the weight of this accomplishment, one must first understand the scientific wilderness from which it emerged, a landscape defined by material frustration and a deep-seated institutional skepticism toward the very substance Nakamura would ultimately master. The pursuit of a commercially viable blue light-emitting diode through the 1970s and 80s had become something of a holy grail in materials science. The existing red and green diodes, based on gallium arsenide phosphide and gallium phosphide systems, were well established, yet the blue component remained elusive. Without it, the creation of efficient, full-color displays or pure white light from a solid-state source was a physical impossibility. The global research community had largely converged on the promising candidate material zinc selenide. This wide-bandgap ILV semiconductor compound possessed a crystal lattice structure that was advantageously compatible with readily available gallium arsenide substrates. Simplifying the epitaxial growth process, major corporations invested immense resources into perfecting the zinc selenide devices, and for a time, this path appeared to be the most logical and likely to yield success. There was, however, a persistent and fatal flaw. The zinc selenide crystal was fundamentally fragile, prone to generating defects and dislocations under the high current densities required for bright emission. These defects would multiply during operation, causing the diodes to degrade rapidly, their luminosity fading to uselessness within mere hours. The material's inherent weakness presented a seemingly insurmountable obstacle. A small, courageous contingent of researchers explored an alternative path, one fraught with its own severe difficulties. This path involved the group II nitride semiconductors, specifically gallium nitride. Gallium nitride possesses an extremely robust crystal structure and a wide, direct bandgap of approximately 3.4 electron volts, making it an ideal theoretical candidate for emitting blue and ultraviolet light. The primary figures in this early exploration were Isamu Akasaki and Hiroshi Amano at Nagoya University. Their foundational work throughout the late 80s was heroic. They contended with the immense challenge of growing high-quality gallium nitride crystals. A suitable, lattice-matched substrate for gallium nitride was unavailable, forcing them to use sapphire, which has a significant 16% lattice mismatch. This mismatch generated a high density of crystalline defects, compromising the material's optical and electrical properties. Akasaki and Amano pioneered the use of a low-temperature aluminum nitride buffer layer, a critical innovation that significantly improved the quality of the gallium nitride films grown atop it. They also achieved a landmark success in producing type gallium nitride, a necessary component for any diode structure, by doping it with magnesium and subsequently treating it with low-energy electron beam irradiation. The work proved that gallium nitride was a viable semiconductor, yet the material they produced remained difficult to work with, and the type conductivity was low and unstable, its mechanism understood imperfectly. The global electronics community observed their progress with academic interest, while continuing to pour its industrial might into the zinc selenide avenue. It is within this context that Shuji Nakamura's contributions, undertaken at the Nikkei Corporation, a specialized chemical company in a remote part of Japan, become so extraordinary. Nakamura, a figure of intense focus and relentless empiricism, approached the gallium nitride problem with a fresh perspective. Unburdened by the prevailing academic consensus, he began by fundamentally re-engineering the primary tool of epitaxial growth, the metal organic chemical vapor deposition, or MOCVD, reactor. Conventional MOCVD reactors had a single gas flow, which led to turbulence and uneven temperature distributions across the substrate, resulting in inconsistent film quality. Nakamura, drawing on his deep intuition for fluid dynamics and materials processing, designed and built his own unique two-flow MOCVD system. This novel design introduced a secondary, coaxial flow of nitrogen gas that stabilized the primary flow of precursor gases, such as trimethyl gallium and ammonia. This created a perfectly laminar flow across the heated sapphire substrate, suppressing parasitic reactions in the gas phase and ensuring a uniform deposition environment. The result was the ability to grow gallium nitride films of unprecedented crystalline quality, far surpassing what had been previously achievable, even with the lattice mismatch of the sapphire substrate. This custom-built apparatus was the first pillar of his eventual success, a testament to the power of process engineering in fundamental science. With superior gallium nitride films at his disposal, Nakamura next confronted the central challenge that had limited the work of his predecessors: the reliable and efficient creation of type material. He confirmed that magnesium was the correct dopant, but observed that as when magnesium-doped gallium nitride was highly resistive, the prevailing theory, which Akasaki and Amano had addressed with their electron beam, was that hydrogen, a byproduct of the ammonia precursor in the marked process, was bonding with the magnesium atoms. This formed electrically inactive magnesium-hydrogen complexes, passivating the magnesium and preventing it from accepting electrons to create the necessary holes for type conductivity. Nakamura sought a more practical and commercially scalable activation method than electron beam irradiation. Through a series of meticulous experiments, he discovered that a simple thermal annealing process in a nitrogen atmosphere at temperatures around 700 degrees Celsius was remarkably effective. This heating provided sufficient energy to break the magnesium-hydrogen bonds, allowing hydrogen to diffuse out of the crystal lattice. The magnesium atoms were thereby electrically activated, and the material was transformed into a stable, low-resistivity type semiconductor. This discovery, elegant in its simplicity, was the second critical pillar. It unlocked the door to fabricating a functional gallium nitride p-N junction, the fundamental building block of a diode. Having mastered both high-quality crystal growth and type doping, Nakamura proceeded to construct a device architecture of exquisite efficiency. Leveraging the principles of heterostructure engineering pioneered by Herbert Kromer, he fabricated a double heterostructure device. This structure consisted of a thin active layer of indium gallium nitride sandwiched between layers of type and N-type gallium nitride. The genius of this design lies in its manipulation of electronic energy bands. Indium gallium nitride has a narrower energy band gap than the surrounding gallium nitride layers. While a forward voltage is applied across the diode, electrons from the N-type layer and holes from the type layer are injected toward the junction. The energy barriers created by the wider band-gap gallium nitride layers effectively trap these charge carriers within the thin indium gallium nitride active region. This quantum confinement dramatically increases the probability that an electron and a hole will meet and recombine radiatively, emitting a photon of light in the process. The recombination process becomes overwhelmingly efficient. Furthermore, by carefully controlling the percentage of indium in the indium gallium nitride alloy, Nakamura could precisely tune the energy band gap of the active layer. This allowed him to select the exact wavelength, and thus the color, of the emitted light. For the first time, brilliant, pure blue light poured forth from a small, robust, solid-state chip. The 19095 paper, Eye Brightness in Garen Blue Light-Emitting Diodes, published in the Japanese Journal of Applied Physics, and related works from this period, announced this success to a stunned world. The reported external quantum efficiencies and luminous intensities, measured in candelas, were orders of magnitude higher than anything previously achieved with either gallium nitride or the failing zinc selenide systems. The immediate impact was profound. For the first time, a complete red-green blue, or RGB, palette of semiconductor light sources was available. This enabled the creation of larger-scale, full-color LED video screens and a new generation of vibrant digital displays. The robustness of the gallium nitride material meant these devices had lifetimes measured in tens of thousands of hours, a stark contrast to the ephemeral glow of their zinc selenide competitors. Perhaps the most significant immediate application, however, was an innovation of pure elegance. Nakamura and his team at Nikkei quickly realized that by coating their high-brightness blue LED with a phosphor, typically a formulation of yttrium aluminum garnet, or YAG, doped with cerium, they could create white light. The phosphor absorbed a portion of the blue light and re-emitted it as a broad spectrum of lower-energy yellow light. The human eye perceives the combination of the remaining blue light and the emitted yellow light as white. This phosphor conversion method became the basis for the modern white LED, a device that offered a pathway to general illumination with efficiencies that dwarfed incandescent and fluorescent technologies. The evolution of Nakamura's gallium nitride technology continued at a breathtaking pace. Following the success with LEDs, he directed his efforts toward creating a laser diode from the same material system. This presented an even greater challenge, requiring near-perfect crystal quality to sustain the optical feedback necessary for laser action and even higher current densities. By further refining his mocked growth techniques to dramatically reduce the density of threading dislocations, and by engineering complex multi-quantum well structures, he demonstrated the first pulsed blue-violet indium-gallium nitride laser diode in 1996. This invention became the technological heart of the next generation of high-density optical data storage. Most famously, a Blu-ray disc. The shorter wavelength of the blue laser allowed for a much smaller focused spot than the red lasers used in CDs and DVDs, enabling vastly increased data storage capacity on a single disc. The work also spurred a global explosion in gallium nitride research. Scientists like Stephen Den Bars and James Speck at the University of California, Santa Barbara, whom Nakamura would later join, built upon his foundations to probe the deeper physics of nitride semiconductors, investigating phenomena like the quantum-confined Stark effect and efficiency droop at high currents, pushing the performance of these devices ever higher. The entire field of solid-state lighting, from traffic signals to automotive headlights to residential and commercial illumination, rests squarely upon the manufacturing processes and device structures that Nakamura established. The reception of Nakamura's work was initially a mixture of astonishment and, from some corners, deep skepticism, given that it originated from a relatively unknown chemical company and overturned the established research trajectory of global electronics giants. This skepticism quickly evaporated as the sheer performance and reliability of the Nikkei diodes became undeniable. The story of its creation, however, became a complex narrative. It was celebrated as a triumph of a lone, tenacious inventor, a narrative Nakamura himself sometimes encouraged. Yet, it was also a story of corporate vision, as Nikkei's founder, Nobuo Ogawa, had gambled a significant portion of his company's resources on Nakamura's conviction. This relationship later soured dramatically. Nakamura's departure from Nikkei led to years of contentious litigation over the intellectual property rights and financial rewards for his world-changing invention. The legal battles highlighted a deep-seated cultural and legal disparity in how Japanese and Western systems valued the contributions of employee inventors. Ultimately, the scientific community's judgment was unequivocal. In 2014, the Nobel Prize in Physics was awarded jointly to Shuji Nakamura, Isamu Akasaki, and Hiroshi Yamano for the invention of efficient blue light-emitting diodes, which has enabled bright and energy-saving white light sources. The prize committee explicitly recognized the inseparable contributions of Akasaki and Amano's foundational university research and Nakamura's industrial breakthrough. In the final analysis, Shuji Nakamura's 1995 work on hybridness blue LEDs stands as a monument to the power of persistent, process-driven materials science. It was a victory not of abstract theory but of empirical mastery over a stubborn material. His direct influences were clear. He stood upon the shoulders of Akasaki and Amano, taking their pioneering proof of concept and, through superior engineering and relentless experimentation, transforming it into a commercially dominant technology. In turn, his direct influence on others is immeasurable, extending to nearly every researcher and engineer working in optoelectronics and solid-state lighting today. The specific techniques he developed, from the two-flow Mach reactor to thermal annealing for type activation and the indium-gallium nitride double heterostructure, became the global industry standard. His work did more than simply give us a new color of light. It provided the key to unlocking a future of sustainable, efficient illumination, fundamentally altering our relationship with energy and reshaping the visual landscape of the 21st century. It was a singular achievement, born of a singular focus, proving that sometimes the most revolutionary path is the one everyone else has deemed a dead end.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.